Hey everybody, how's it going? We're going to go over LeetCode question 230, Kth smallest element in a binary search tree. So you're given the root of a binary search tree and an integer k. Return the kth smallest value of all the values of the nodes in the tree. So a binary search tree is a tree where all the nodes to the left of the root are smaller and all the nodes to the right of the root are larger. So in this case, you can see 1 is less than 3, 4 is greater than 3, and down here 2 is greater than 1 because it's to the right of 1. And it's asking us to return the first smallest integer in this case, and that's just going to be 1. And if you go down here, it's asking us to find the third largest or third smallest integer in this tree. And it's pretty easy to tell that's going to be 3 because if you start at the bottom left corner where all the nodes are going to be pretty small, and you climb back up the tree, it's going to give us 3. So what I think about is an in-order traversal, because that's going to help us maintain the sort of all the elements, right? So an in-order traversal is one of many ways of traversing a tree. In this case, it asks us to traverse the left subtree first. So we're going to start from the root and then keep going down until, we reach a none. So no more left subtrees. And we're going to have some array here that keeps track of all our elements. So if there's nothing to the left of this node, then we're going to add the value that we're at. We want to add the value we're at first before looking at the right subtree, because we know the value we're at is going to be less than the right subtree, and we want to maintain that sort. And we see there's nothing to the right, so there's nothing to add there. We just go back up the recursive call and then add 2. Then we go back up and add 3. And before we try to go back up to 5, we want to look if there's a right subtree, which there is, and then we want to add that. Then we finally go back up to 5. And at this point, we completed the entire left subtree of 5, and all there's left is the right subtree, which is 6. Okay, so that's our last node. And using an in-order traversal, it's pretty easy to find every node that we're at and then append values to the list. And say we want the third largest or third smallest element, then all we have to do is return the index at k-1, because this is a zero-based index data structure. So that's going to be, if you start at 0, 1, 2, we want to return this element. And if this is 4, we want to return k-1, which is 3, so on and so forth. It's pretty simple. Okay, and if we want to code this up, we're going to create an empty array and then define our DFS function. It's just going to take in the root and the array. And for every recursive function, we need to have a base case that stops the recursion. In this case, it's going to be when there's no root, we just return. Otherwise, we want to do recursion on the left subtree. So we're just going to call DFS root.left and then the array. And after we're done traversing the entire left subtree, like we did in this example, we want to append the value we're at to the list. So what we do here is just say array.append root.val. Okay? So that's good for the left subtree. Then we have to look at the right subtree. Right? So we're going to just copy this. And it's the same logic, just take this and make it right. And after all that logic is done, you can just return. Okay, and outside of the function, we just want to call DFS root and array. And this is going to populate our array with all the values we need. So the last part is just creating a variable. Let's just call it Kth Smallest. And then we're going to look at the array and get the k-1 element from there. And we're never going to get an array index out of bounds because it's guaranteed k is between 1 and the number of nodes in the tree. So we're never going to have some sort of issue regarding that. And finally, we just want to return Kth Smallest and give this a run. Okay, that looks good. Let's submit it. All right, everything looks good here. So time and space, we're going to use O of n space because we're adding all of the nodes in the tree to the list. And the in-order traversal is also O of n. The reason is we're looking at every node in the tree and we're just doing some logic on that. So that's basically what in-order traversal is and how it applies to this problem. Hopefully this helps, and I'm going to make some more videos on binary search trees and then probably graphs in the future because I think I'm getting pretty good at this, so I'm going to try to switch things up soon. Thanks for watching.